Good morning, everyone. My name is Bhanuteja, and I'm studying in CSC Regular First BTech First Sem in JNTUH, Kukatpally. And my assistant professor for BW subject is G. Raju sir. Alright, so let's begin with. Today my topic is construction and working of a DC machine. So first we'll discuss our agenda, which is we'll be discussing about what is a DC machine, construction of a DC machine, types of DC machines, working of a DC machine, and a couple of examples and applications of DC machine. So first, what is a DC machine? A DC machine is an electromechanical device which is used to convert electrical energy into mechanical energy or vice versa. The DC machine is used to convert electrical energy into mechanical energy is known as DC motor, and then there's another type which is DC generator which converts mechanical energy into electrical energy. Now the same machine can be used either as a motor or a generator. Basically, the construction of the machine is similar for each case, but the working of it and the functions are completely different. So first, let's discuss about DC motors. DC motors, as you can see on the top right, they have as a construction of a DC motor. The main four parts are field system or stator, armature, commutator, and brushes. And here, down here on the right is an example of a DC motor in real life. So now let's discuss about these parts of the DC motor. So first, a stator. What is a stator? A stator is basically the stationary part of a DC motor around which coil is wound and produces magnetic field. It also consists of field winding, pole shoe, yoke, and pole core. Next, we have an armature. An armature is a rotating part of a motor which generates mechanical energy. Armature core has windings. Next, we move on to commutators, which are periodically reverse the current between the armature and the circuit that produces steady torque. Next, we have brushes, or often known as carbon brushes, which are made of graphite. In the DC motors, brushes supplies the current to the winding of the armature. So that's the main parts of DC motors. Next, we have DC generator. Now, there are main components of a DC generator as yoke, magnetic field system, armature core, armature winding, commutator, a DC generator commutator function, a shaft, a pole shoe, poles, and bearings. Now, as you can see, the various parts of the generator are similar to that of a DC motor. So next, now we'll discuss the parts and their functions. Now, main four parts of a DC generator are yoke, DC generator commutator function, bearings, which we didn't discuss about DC motors, magnetic field system. So first, what is a yoke? A yoke is basically the outside frame of a DC generator, which is a hollow cylinder made of cast or rolled steel. Next, we have magnetic field system. It is a DC generator's magnetic field system as its stationary component. It generates the primary magnetic flux in the generator. Next, we have DC generator commutator function, which is the basic purpose of the commutator is to convert DC to AC. It functions as a reversing switch, and its purpose in the generator is to ensure the current flowing from the generator continues in the same direction indefinitely. Next, we have bearings. Bearings are used in a system to ensure that the various parts of a DC machine move smoothly. Hence, the system's components require less frequent greasing and last longer. Now, as we discuss the construction and parts and the main parts and the explanations about DC motors and DC generators, we'll be moving on to working of a DC machine. So now first, when a current carrying conductor lays in a magnetic field, the magnetic field produces a mechanical force on it, and that is known as torque. This rotates the conductor coils in a magnetic field. The direction of this produced torque can be found by the Fleming's left-hand rule, and we all know what the Fleming's left-hand rule is. The thumb indicates the direction of force, the magnetic field, the index finger, and the middle finger is the direction of current. And I'm pretty sure we all know what the left-hand rule is. So now we want the direction of force, as we mentioned before, and the direction of this produced torque is found by the Fleming's left-hand rule. Next. Now, so as you can see on the top left, here's a brief picture about how a DC machine actually looks like in circuits. So I'll be explaining the working of a DC machine. First, there's like 8 steps in total. So the first, a current-free conductor is placed in a magnetic field, and there's an air gap between the north and the south poles. So the magnetic field does not directly flow through the conductor. So as you can see, there's south and north poles, and as it says, there's an air gap. There's an air gap, and the magnetic field does not flow through the conductors, is what it says. Next, a current starts flowing through the conductor as the conductor is not connected to any supply. It generates its own magnetic field. Right. Next, we have the magnetic field generated by the current in the conductor follows the corkscrew right-hand rule. We use Fleming's right-hand rule for that, with the magnetic field line circulating clockwise around the conductor. Next, the fourth point, the conductor is placed in a main external magnetic field. The magnetic field produced by the current in the conductor interacts with this external magnetic field. So those are 4 main points of the working. Next, we have 4 more right here. Next, the magnetic field due to the current in the conductor aligns with the external magnetic field above the conductor, resulting in an increase in the magnetic flux in that region. The combined effect of the external magnetic field and the conductor's own magnetic field creates a force that pushes the conductor downward. Next, below the conductor, the magnetic field generated by the current opposes the external magnetic field, leading to a decrease in the magnetic flux density in that specific region. Lastly, if the direction of the current in the conductor is changed, the flux will accumulate downwards and will try to move the conductor upwards. So that's the working of a DC motor. DC machines, any. So now let's move on to the formulas for force, torque, and EMF of a DC machine. These are major formulas which we want to discuss. So first, let's go for the force conducted by a conductor, or experienced by a conductor. Now we know F is equal to BLI sin theta, where B is the flux density, magnetic flux density. Then we have L, which is the length of conductor. And then we have I, which is current flowing in the conductor. Then sin theta, which is the angle between the conductor and the magnetic line of force. So that's the force experienced by the conductor. Next we have the torque. Now basically torque is the force that tends to rotate or move an object around a central axis. It's given by torque is equal to 0.159 P5 mv by A whole into the IA, which is nothing but armature current. So as you can see here, T, which is torque of armature, IA is the armature current, P is the number of poles, and phi over here is flux per pole, N is the speed of motor measured in rotation per minute, RPM, Z is the number of conductors, and A is the number of parallel paths. Next, we'll go on to DC motor speed, which is given by KEB by 5. And we already know that N is the speed in RPM. K is a proportionality constant, which is equal to 60A by GB. Next, we will move on to the EMF of the DC machine. EMF, or electromotive force, is responsible for the flow of current in electrical appliances. EMF is the electric potential and is produced which counters the armature current. So now EB is equal to P5 NV by 68. And if you see, it's probably similar to the torque and DC motor speed. because it's derived from those two formulas. And the same thing here, P is the number of poles, phi is flux per pole, N is the speed of motor in RPM, and Z is the number of conductors, as well as A is the number of parallel paths. So these are a few major formulas that we get from DC machines. These are calculation of torque, force, and EMF, and also the speed of the motor. So lastly, we'll be discussing about the applications of DC machines. There are many major applications. Few of them are used in traction work, machine tools, industries, and elevators. Next is also used in speed compared to other motors, as it has the widest variation. Next, DC motors have a very high starting torque, and that is why it is used to start high inertial loads such as trains, as in goods trains, and elevators, etc. So yeah, that's about it of applications and workings and constructions of a DC machine. Thank you.